Hi, and welcome to my presentation of my solution to Lab 1, where we were supposed to solve a maze with the help of A-star algorithm. I think my thought was to begin with my code, show it a little bit, and explain how I have thought. So, I begin with, well, making of the maze, and we got uh, well we got the algorithm to start with, which created a maze, and quite early I saw that this algorithm and the maze that it made was in fact only a long string, so it was quite hard to work with. So I thought that I would try to make it into a two-dimensional array instead, which is much easier to work with. So, and with a two-dimensional array, you also have the possibility to have x and y coordinates. So you can have coordinates for each room or cell node in the area you want to work with. And what this code does that we got is that it makes a room with walls between every room in this area. And so I made a maze too, which is in fact only an area with empty rooms, but it has walls between all the rooms. And in fact, I take in my width and height, and then I generate an empty array, which will become my maze. And then I append for the height, I append empty elements into my array, and then into each element I append the width of the area which I'm to work with. And then I give each element in my finished area a number, which number 1 represents a wall, and a 0 represents an open room. So each room and each wall is a part of my area which I will work with. And then I return my maze back to the maze generating algorithm. And here, where the algorithm randomly jumps around the maze to tear down its walls, I have put in my own maze too, so it does the same thing. It tears down the walls in my maze, which contains of a big space with rooms and walls between each room. So it follows the original code and just replicates what that code does, and also makes a copy of the original maze, so to say. And then I made a nice maze, which also was a copy, just to see that it was exactly the same. I don't work with this because this maze, it is an array, but it contains the same characters as the original maze. So just to see that it was in fact a replica. Then I draw my maze just to see that it looks okay, and then I return my maze to the original program. And the original program is down here. This is my main, and there I also set the width and height of the area I am to work with, and set the array width and array height, which is not the same as the original because I have to count for the walls and everything. Then I set a start position and an end position. So I always have start in the top left and end in the lower or bottom right corner. Declare my maze. I declare my nice maze too. And then M, which I will come to later in the presentation. And I thought I would just show a breadth first search, and I can show it with an empty room here, just to show what it does. It does the breadth search of everything in its search for the end. It found the end, and what it does is just shows a way it found. It found one way to the end. There are of course multiple ways, but this one found one way it thought was good. And I also can do it with a maze and show that it searches every front at the same time. It goes quite fast, and when it has found the end, it backtracks to the beginning. So my breadth search, in fact, reminds of a Dijkstra search. It does almost exactly the same thing as a Dijkstra search, but it works, and I'm happy. So that was the first one. I also have a depth first, with which searches, well, a depth. Here is my breadth first, but we were only supposed to talk about A star, so I just talk about the breadth quite fast, I thought. But it searches every node in the front that it can find simultaneously, and adds it to my M, and I create M, which is in fact an empty space where I store every location in that space. There I store, in the breadth first, I store my count, my step count. And when I find at the end, I backtrack the step count to the beginning, in short terms. My depth first is a little bit different. It also creates an M. I think I create an M in every instance just to keep track of every node I have searched or looked into. And here too, it has a front. It searches the front. Here I have a front found just to make it a little bit faster. If it finds an empty space where it can go, it compares the maze to see if it's a 0, then it's an open room. If it's a 1, it's a wall, so it can't go there. But if it's a 1 and it haven't been there before, because the M array is also consists of zeros, if the program or algorithm hasn't been there before. So it looks into that, and then if it can go there, it puts that one to the front and puts the count to my M array. If it already has been to that part, or if it already had found a way to go, then it will store this new, it searches all directions, all 4 directions. And then if it has found a direction which it can go, and it wants to go because it's depth first, then it stores the other possible direction in a temporary front, which it later can call. If it comes to an end and it can't go any further, then front will be empty, and then it will pop from the temporary front to the front and go from that temporary location, and it will set back count to the actual value in that location. And this continues in this while loop until the length of front, well, until front is empty, and until the end is empty too. So and then it prints out the result. I can make my depth first in the maze, and it only searches one way. every time. Now this one will find the goal quite fast. And there. And here it shows the path it found to the goal. But now I will talk about my A-star search, I thought. And A-star, it creates a class node for each position, where it has its own position, its parent, and then it has its F, its total cost, so to say. And then it has its G, which is the step count from start, how long it has gone. And then it has its H, which is the distance from the current from this node to the end, the heuristic distance till the end. And then I set my start node and my end node. And I set the positions to start and end. And then I just set everything to 0. I create my M again, which I found quite good to work with. I guess a lot of people have copied work or found finished solutions on the internet. I looked a bit too, but I didn't want to copy too much, but I rather wanted to figure it out by myself as good as I could do. I've seen examples from some people which have very short code, and well, this code isn't so short, but it was what I could come up with in this time frame, and it works quite good. So I'm quite pleased with it, though I can of course make great improvements, but in this time frame I'm quite happy. So I have my end y and xy, and I just set those because it was easier for me to work with and have track of those. Set my count to 0, total cost to 0, and distance to 0. And then I make my front, which is an empty array, and then I append to my front my start node, make my path total, which contains my whole search, which paths I have searched, not only the ones which is the best, but all paths I have searched. And then I set found to false, which is if I have found the end. And then I start my while loop, and it continues while front still is open, or while front have nodes in it, and while I haven't found the end. So, and then I copy to my current, set that to my first front position. I copy my front 0, set index to 0, and then I search my front for the node with the least F score, so the least total cost with consideration to distance to goal or end and steps taken so far. And if I find a node with a lower F score, then I copy that one to my current. And when I have looked through my front, I set the index to. When I have looked through my front, I then have my know which index in front that's my node with the least F score, and I pop that one to my front. Set my X and Y, and then I search in 4 directions. So up, right, down, left every time. Set my ty and temp y, temp x to my current position, and then plus that search direction. And I compare with my generated maze, which has, if I make a maze with walls and such, it's a copy of the original maze. So I look into that if it's a 0. If it's a 1, it's a wall and I can't go there, so I don't have to do anything. But if it's a 0, then I set my count to the current, plus 1 because I'm about to take one step. I count out the distance from the new node that I'm investigating. I count the distance from that one to the end via this heuristics. And then I count the total cost, which is my count to that node so far, and plus the distance to get the estimated heuristic distance to the end. And then I create my temp node with the new position. I have my current as the parent to that node, and then I put in my calculated values. And if the new node, the temp node, has the same position as end node, then I append that to my total path, append it to my M table or M array, and then found is true, and I break out of the for loop because I'm done. And then it exits the while loop true because I found the end. So then it's finished and jumps down. But if it's not the end, then it goes further. And if the new, it looks if I have been here before. If I haven't been here before, it appends, it sets my M at that position to my temp node. So it gets the temp node's all values. Append the temp node to the front because I'm about to search that one next time. Or if it has the least F value, but I append it to the front. And also I append it to my total path. So I know that, so I can see my total path that I have looked into that node too. If in fact I have been to that node before, if it goes around in a circle or some weird way, then M will not be, .g will not be 0. It will have another step count. So then I compare if my new node has a lower step count than that the node I have been to before, so to say, and stored in my M. Then I replace my stored node in M tytx with the new temp node because that's better. And then I append it to path total. And then I continue with next iteration of the for loop. If the new node has, if my temp node has a bigger G, a bigger step count, which means that I have gone in a circle and then some ways back to where I was before, then I set my current dot parent to the old node because then this is a shorter path. Instead of going around in a big circle, I can take this shortcut instead. It's a shorter path. And I set my current .g, the count, the step count, to the one that was in the old, which I was looking into, plus 1 because it's a step further from the old one. And then I count the new total distance or total cost for this. And then I set my current, which is stored in M already, but I set that to the new current values. And if nothing of this is true, so to say, then I add my temp node to my M if it's not found. So I add it to my M to keep track of its position and its parent and so on. I add it to my front because I want to look into it next time or sometime. And then I add it to my path total also. And for each iteration, I also draw I make a path plot from my total path, clear my output, and then draw a new image from my path plot which is all the total paths so far, so I can see my search in real time while it's iterating. And when I have found end, then it goes out of the while loop, goes down, makes an empty path array, and then it appends my end to that array, and it sets my current location to the end and my total count to 0. And while it starts a while loop, and while my current position is not start, then it iterates through the loop. So I have appended my current location to the path, which is the end, and then I look into set my current location copies the current location's parent into it. And then my path appends my current location's position. And then my current location has become the parent to the earlier. And I add my count because I have taken one step back towards the start. And then it iterates over this, and it appends the parent all the way back to the start. Then I clear my output, print a couple of things, print my total path searched, and then I print my path found, which is the shortest path, and then I also print my total count, step count. So I thought I would show this one. Here we have the depth search, but then I thought I would show my A star as good as I could do it, at least. It only searches the most reasonable way all the time with the shortest F total cost, and there it found the end. And here I can see every path looked into. It looked this way, but this way was better, so it gave up this way for that time, continued, looked this way, but this was better, so it continued, looked up, this was still better, and all the way to the end. And here is the shortest, or in this case there is only one path, so but this is the path it found from start to end, and it had a length of 80 steps in total. I have made a couple of tests also we can make with no room, just to see that it goes, and here it sees that this is a closer path. So I've done some tests to see how it acts in an open room, in the maze, and so on and so forth. The thing I have noticed is I think to be able to search in a maze, you have to have slightly different algorithms if you search a maze or if you search an open room, I think, because it doesn't. If I search a slightly different room where I put the badass wall in the middle of everything, it doesn't get it. It tries to search the best path. It reminds of a greedy search, but it goes back to find the closest way, and then it's on the go again. But it doesn't break here. I saw some videos where they had, I guess, I read about tree search and graph search, and I guess a graph search maybe is the one that starts to build this way too, to find the closest way. But that, I don't think that would be efficient in a maze. I only think that one is efficient in an open space. But I'm quite pleased because my algorithm works perfectly in a maze, and it works at the same time without any modification. It works quite good in a little trickier environment, but still I think it performs very well the maze. It was quite challenging. As I said before, I wanted to figure it out by myself instead of just copying things from the internet. And I think it went well, quite well in the end. So, well, I don't know if I have anything more. So, thanks for me, and I hope I hope this is okay. Have a good time. Bye.